Oops. Question 9 about momentum. So we've got a diagram shows a rocket to try to change the path of an asteroid. So it looks like it's going to try and push it away from hitting the Earth. That's a good thing. The rocket has a mass of 5.5 kilograms. It's traveling to the right at 14 kilometers per second. Calculate the momentum of the rocket in kilogram meters per second. So I can see the kilograms is matching up with that, but the kilometers per second does not match up. So times that by 1,000 and we get 14,000 meters per second, and then we're away. We've just got to times them together. So that will then give you 7.7 times 10 to the 9, answer C. Next part, the asteroid has a momentum of 7.5 kilogram meters per second and a mass of 8.0 times 10 to the 6 kilograms. Fine, they speak to each other. We're happy with that. And then we're going to need the formula. I taught you magic puking vampires with delta P being momentum. We've got to calculate the velocity, so speed with direction. And there we go. So V equals delta P, I've missed the divide sign out there, divided by M, 7.5 times 10 to the 10, divided by 8.0 times 10 to the 6, gives me 9.4 times 10 to the 3, or 9375 on your calculator. On to the next one. Long question and a tricky question. I'll try to do it as quick as I can, but without rushing it. A student wants to investigate the effect of crumple zones on the force. Okay. So that's going to be using what we said is F delta P T. Okay. So what was it? Frogs, puke, tarantulas. The student has one trolley with a spring. So there we go. And another without. So clearly this is the one with a crumple zone. This does not have a crumple zone. Let's X through that. Next part, then we can see the trolley at the top. There's the ramp, and then we've got a millisecond timer, and we've got a piece of silver foil. And obviously when that silver foil is in contact with this silver foil, the timer will run. That will give us this. Clearly we can work out the momentum because we know from the previous question that momentum equals mass times velocity. So either they're going to tell us the masses or tell us the velocities, or they're going to ask us to work it out. So after the trolley release, it accelerates down the slope, bounces off the wall. The speed of the trolley can be measured just before the collision with the wall. Okay, so it's saying we can take velocity as being measured for us. The silver foils are connected to a millisecond timer. That makes sense. They make contact, so we can know the collision time. Brilliant. So that's this part. That's the collision time. Explain how the student could investigate the effect of crumple zones. So clearly the question is, how can I tell that the force on that with a spring or with a crumple zone is different to that? The obvious answer is, well, run the one with the spring 3 times down the ramp, collect your results. Do the same with the trolley 3 times down the ramp without a spring, and then we're good to go. So we need to show how we're going to determine force. It's going to be using that. We'll use the one at the back of your booklet. You may wish to refer to an equation. That's you will. How the effect of the crumple zones may be shown. So I said to you, 0 people have ever died going quick. They've all died stopping quickly. So we should see that the force goes down if the collision time goes up, and vice versa. Short collision times, big force, not a good thing. So what precautions to achieve accurate results? So that's just going to be what are the things that we're going to control in the practical. So I'm now going to, hopefully the little bits in red are not going to interfere what I've put. So you go to the back of your booklet and you've got F equals mv minus mu over t. That's the same as your delta, your change momentum divided by time. And because the truck's starting at 0, I could have got away with it by just saying it's mass times velocity divided by time equals the force. Any of those, but I've put the one that's at the back of your booklet. So clearly it told us that it's going to give us the velocity. It says that in the question. So the extra bits I need the mass using the digital balance, because I need to check that the 2 trolleys actually have the same mass. Obviously because one's got a spring which might affect it a tiny bit. Then we need the impact time using the millisecond timer. So however long those silver foils are touching, that will give us the impact time. So the next part is, well, what am I going to do? Well, I'm going to repeat the experiment 3 times. One with the spring, the crumple zone, and then another 3 times without. And then we will account for any change of mass because of the spring. Then measure the contact time of each and then put that into the equation F equals mv minus mu over t. Perfect. So mass times final velocity minus mass times initial velocity divided by time. It's the same as your change momentum over time. Next part. Well, the spring one should have a longer impact time, 1 mark, and therefore should have a lower force. And then I think we've answered most of those parts apart from the precautions. So the precautions are, let's go through accurate results, repeat and calculate a mean. Make sure we control the following, same starting position exactly. Make sure that the slope or the slope angle is the same every single time, so there's no change in accelerations. And make sure there's no additional push or force, again, because that would change the acceleration. So that's it in a nutshell. It's a long question, it's a tricky one. And then on to the next one. Newton's third law, when applied to the collision of the rocket and the asteroid, is shown as below. So that's Newton's third law. Explain how this statement links to the conservation of momentum in the collision. So we're going to have to talk about Newton's second law as well. So my job now is to talk about, well, we know Newton's third law. My example of that was if I'm leaning on a wall, then we've got my force on the wall is equal and opposite in direction to the force of the wall on me. And we learnt this as interaction force pairs. Two forces between two objects that are equal in size and that's not particularly good, I'll do it that way, and opposite in direction. So the next part is, well, we just got to say, where on earth does that mv minus mu divided by t come from? We're just going to show that we've got Newton's third law, so we're going to link in as well the equal and opposite in terms of conservation of momentum. And conservation of momentum is the idea that the momentum at the start of any collision is the same or equal to the momentum at the end of a collision, assuming no other forces are involved. Okay, so there's no other external forces. So to go over this then, well, Newton's second law is F equals ma. Next part, well, we know that A equals V minus U over T, so we can combine those for these. So you can imagine now we've got, well, F equals M times A. I'm now going to swap A to V minus U over T. And now we can see, oh yes, I get exactly where that equation comes from now. F equals mv minus mu all divided by t. And that just says that if the forces on a object are unbalanced, the object will accelerate. And what we're going to see is that when we have these forces, the momentum will be conserved. Oh, I lost my train of thought there, sorry. So the next part now then is, what do we know? Well, the collision time for both will be the same. We've got that from this equal and opposite forces exerted by the asteroid on the rocket. And therefore they're both going to share the same collision time. They must do. Therefore the change in momentum is same for both, as the forces on each other are equal in size and opposite in direction. And that's now linked straight back to Newton's third law, which is what they've got there. So we know that they're the same. And that's all we're stating. We're writing that bit in black by saying, and they are the same on each other. So momentum at the start is equal to the momentum at the end, and no external forces were applied to the system. That's for 4 marks. So tricky 4 marks, that.